Hello, welcome. This is Side A, Side B. In this video, supplementary material for inverse series. We're talking about the Lambert W function, which is an inverse, then doing an example. The function has to do with expressions of the exponential form, so we thought this would be a change from doing examples using straight-up linear functions. We hope you'll stick around. Previously, we solved a nonlinear equation using the said function, so overall, this video will be an updated version of that video. In order to solve, we had to rewrite the entire equation in a particular form, and then we used the inverse to solve, which is called the Lambert W function. No, not literally a W, as in two sheep. Although we do have a double of something. Bah! Hopefully good. In this version 2.0, clarifying the Lambert W function in terms of previous work and clarifying notation. On that note, first a brief discussion on the said function, compare it with the work we did so far to help our understanding. The first blue bullet. The equation in the gold box is in the context of the Lambert W function, which is defined as the inverse function of g of omega equals omega e of omega. Second blue bullet. So the Lambert W function is denoted as capital W of z. If we let z equal the following expression, returns W of z equals omega. Because we know composing the inverse with g of omega will just return the original input omega. Next, consider the given equation gold box. Notice the right side is the Lambert W function. In the second blue bullet, g is composed with its inverse, which we know will return the identity function. The logic is the blue notation. F of f inverse of y equals f of x equals y. Last blue bullet, we have f of w of z equals the Lambert W function. Since the input of f is unchanged, so f must be the identity function, which we know is the logic of the blue notation. Identity of f of x equals f of x, because the identity function preserves the original input. To help our understanding, we'll just make a comparison with the notation. We have g of omega equals omega e of omega, which can be written as z equals omega e of omega. Similarly, we have f of x equals x plus 1, which can be written as y equals x plus 1. Second red bullet. If h is the inverse of f, we know h of y equals x, or h of x plus 1 equals x. Second blue bullet. W is the inverse of g. Then we know w of z equals omega, or w of omega, e of omega equals omega. See that? We can also consider g of omega in general terms. Orange bullet. We can define a function f of x equals x e of x. And the inverse of this function is the Lambert W function. Then we have w of y equals x, because f inverse of y returns the original input x. Next, we can define a function f where set y maps to set z, and its inverse w where set z maps to set y. Then we have the rule f of y equals y, e of y, and its inverse y equals w of z, yellow box. Then consider the orange bullet. Our overall plan should be to solve for the equation white box. We must rewrite it in the form blue box. Then we'll use the facts, yellow and green box, to isolate y to solve, which will modify to the yellow box. Now consider, more specifically, we want the second blue box, which is the same form as the first, just the variables have changed. By letting y equal x times c for some constant c, and z equal lowercase phi. Then let's solve for y, and then we can solve for x. First column, first bullet is a parent. Second orange bullet, we use the facts of the yellow and green boxes. We apply the Lambert W function to both sides. Second column, y is solved. X times c equals w of phi. Now we can solve for x by dividing each side by c. So again, if we can rewrite the white box in terms of the second blue box, we can apply w of phi to solve. See that? In our case, we want a product. For this version, the previous video is edited. We have the original audio which goes with solving the white box, but in this version, we have new blackboards. So without further ado, let's get started. Alright, so let's tackle this equation. And recall, ln A plus ln B equals ln A times B. And that's what we're going to be using. That's the addition rule for logs. Ln 3 to the x plus ln x squared equals ln 5. You all know that. Whatever we do to the left, we got to do to the right. And that x was actually hiding there, but we uncovered it there. It's just equals, because of the addition rule, x squared, 3 to the x, is just a product, which is very nice. It's an equation now that we can deal with, a friendly equation. Now remember, the natural log has a base e. If we take the e of both sides, we'll unpack that equation. Now, it's a different equation for sure. X squared times 3 to the x is definitely different. It's a different equation. So we can definitely ask, do those two equations, well, they don't equal each other, but do they equal each other for 5? Can we use those two equations? Will x be the same for those two equations for the value of 5? That's what we want to discover. So those, it's going to be fluke if those two equations equal each other. So what we want to find is if those two equations intersect when x equals the same value for when y equals 5. So the first thing we're going to be trying to take care of is that power. And then next we're going to be taking 3 to the x. Let's take that power. Let's deal with that power. And for that, we can square root each term because of the property of square roots. Because the left-hand side is a product, we can distribute those square roots to the individual terms. Nice. That means that is way better. Now that power is gone. And we have a square root of 5. Now that square root of 5 has a plus or minus, should have a plus or minus sign on it, but to save some time and some notation, to avoid some confusion, we're going to just leave that out. And if you recall from also the property of exponents, that square root we can just times it with x, and then the exponent is x over 2. Also to avoid confusion for that radical. So if you recall the Lambert W function, the term on those are the two terms that we want to make equal. And if you notice, in the exponent, there's a half. So we have to divide the half. We have to divide the x with a half. And we have to do the same on the right. All right, now we can start to do more work on the equation, and we have to take that x over 2 exponent, we have to free it from the top. And then, to do that, we'll use e to the ln (3) equals square root of 5 over 2. Now, if you notice, so yeah, we've taken the x over 2 exponent down. If you notice, now it's times with ln 3. We're getting very close. So now we have to times the bottom of the left with ln 3. And then times the right with ln 3. Like so. All right. Now remember, ln has the same, it has the base of e. And now our expressions equal each other. We have phi equals phi. Beautiful. Now we can solve for x equals w of 5. And we're left with x over 2 times ln 3 equals w of ln 3 times square root of 5 over 2. Nice. And now, everything here on in is just straight up algebra. That ln 3 can be brought over. Have that term over ln 3. And the 2 cancels. That 2 can be brought over. Beautiful. We're left with the x equals w of 5. And the equation is 2 times w of ln 3 times the square root of 5 over 2, all over ln 3. Our x, and there you have it, ladies and gentlemen. Our x is finally isolated. After that detour, that loop, and doing all that studies.
We finally got here. And now, it's just a matter of checking our work. So in the end, do we have x equals w of 5? Now we're just implying w of 5 equals that equals our equation, our entire equation. Let's check our work. We used Wolfram, and the input is the same as our equation. 2 times w of square root of 5 over 2 times log 3 all over log 3. And x equals 1.173 and is a decimal. That's not surprising that it's a decimal. Next is the equation that we used. And take a look. The blue and the orange curves intersect. That's what we wanted. Checking our work on Mathway. If we plug in that value into our equation that we used, we get a value of 4.99, and it's an approximate value. That's the value that we're aiming for. If we plug that equation into our original equation, we get another approximate value. That's working. And it's been an absolute pleasure to bring you this video. See you in the next one.